Hi class, today we're learning about the reciprocals of trig functions. So if you remember from our previous knowledge, the reciprocal is just when you take, instead of sine theta, for instance, we're going to do 1 divided by sine theta. So all of the attributes we learned with reciprocal functions in chapter 5 will now apply to trigonometric functions. Okay, so the first thing we're going to do is go over this chart here, which I just realized I didn't actually print to SmartBook. But while it's doing this, you can copy this down. So remember, if something is an x-intercept or is 0 in the primary trig ratio, that makes a vertical asymptote in the reciprocal because you would be dividing by 0. Anywhere where a trig function is positive, the reciprocal is also positive. And anywhere where it's negative, the reciprocal is also negative. Okay, the intervals of increase on a trig function would be the intervals of decrease on its reciprocal. Okay, that's because if sine is going up, 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 like let's say 1, 2, 3, its reciprocal will be going down, 1/1, 1/2, 1/3. Intervals of decrease, however, would be intervals of increase in the reciprocal. If a point is xy, that new point will be x1/y in the reciprocal, and a local max of xb will now be a local min of x1/b. A local min of xb will be a local max of x1/b. This is due to the intervals of increase and decrease switching. A max occurs when we're going from a decrease to an increase, but in the reciprocal, that will be an increase to a decrease in the same space. So that's why it turns into a minimum. Okay? So the points of intersection of any of these, if you can recall from chapter 5, just when you thought you were all away from that stuff, will be any x values where the y coordinate is 1 and any x values where the y coordinate is -1. So we can start with cosecant, which is the reciprocal of sine theta. So first we want to identify our zeros, and those are the places where we will have vertical asymptotes, okay? Because now we'll be doing 1 divided by 0. So here at 0, we have, here at 0, we have a vertical asymptote. Okay, and then here again at pi, okay, so this is pi over 2, and then at pi, you'll see it's just over 3, 3.14. At pi, we have another vertical asymptote. And then again, here at 2 pi, we have another vertical asymptote. Okay, and then again here at 3 pi, we'll have another vertical asymptote. So notice that vertical asymptotes on the sine curve are occurring at even distributions of pi. So x equals 0, x equals 2 pi, or theta equals, sorry, I should say theta. Theta equals pi, theta equals 2 pi, theta equals 3 pi. So for every integer multiple of pi, you will have another vertical asymptote. Okay, now we also know that the points of intersection happen where the y value is 1 or -1. Well, that just so happens to be the max and the min of sine. So they're going to have a point of intersection here, a point of intersection here, a point of intersection here, etc. Okay, so then we think about, well, what's going to happen here? Well, in this section, sine is positive, but it's increasing. So that means that 1/sine will be positive but decreasing. So what it basically means is that it will create a shape kind of like this. Okay, which should be much smoother, something more like that. Come on, Weens. So erase that weird thing I just did. Let's try this again. More like this, okay, approaching the asymptote. And on this side, it will, again, this is decreasing, so it's going to be increasing up to the asymptote. Okay, here it's decreasing and negative, so it'll be increasing and positive. And now it's negative and increasing, so this will be negative and decreasing. So basically, it's just this repeating set of kind of what looks like parabolas, and that goes on for all eternity. And there you go, that green is the graph of cosecant theta. So you'll notice if you go to GeoGebra and actually graph this. So f at x equals cosecant x. You'll notice if we zoom out that that's exactly what it looks like, just a repeating set of these weird, almost parabola-looking shapes. Okay, so now we can try the graph of secant. So secant is just the reciprocal of cosine. So it's almost the exact same thing. Everything's just shifted over. So the first thing I'd like you to do is label your vertical asymptotes, and then go ahead and draw the rest of the graph on your own, and I can check it for you in class tomorrow. To verify your work, guys, just go to GeoGebra and make sure that you drew it properly, okay? Now, the graph of 1 over tan theta is pretty strange, I'm not going to lie. Notice that anywhere where we have an x-intercept, we're going to have a vertical asymptote again. So this will go here, and at pi, and at 2 pi. Oops, that wasn't shown very well. 2 pi, it's hard to do this. 2 pi, etc. This is 3 pi. Okay, so I'm just going to do it for here and kind of ignore that last part. Okay, now what, though, does the rest of the curve look like? I'm going to use red. So it can't go through that point, but notice that there was an original vertical asymptote here. So what do you think that means for our new function? Well, that means that that is actually going to be an x-intercept, okay? Because vertical asymptotes are x-intercepts, and x-intercepts are vertical asymptotes. So this was pi over 2, and now it's going to be a 0 there, so an x-intercept. And here there was an asymptote, so that's going to be an x-intercept. Here there was an asymptote, so that's going to be an x-intercept, etc. Okay? So now think about it. This, and they're going to intersect at all the values where y is 1 or negative 1. So you can already plot all those points to help you visualize where it's going to go. Okay? So think about it. It is positive and increasing here, so we want it positive and decreasing. So basically it's going to come along, do a weird little like almost cubic shape, and then approach the asymptote. Again here, it's just going to repeat the same exact pattern again and again. So basically the graph of cotangent just looks like a backwards tangent, okay? And so now that repeats over and over and over. So if you go to GeoGebra, you just go cotangent x, you'll see that that's what that does. Just the same graph over and over and over again. Okay, so what you folks need to be able to do as a result of this note is to create the graph of any of the 3 primary trigonometric ratios, and then use your knowledge of reciprocal functions to come up with the reciprocal function in graph form, and to be able to describe why any of the features are what they are. For example, why it's positive, why it's increasing or decreasing, etc. Okay, so now I'm just going to answer 2 very quick questions. Example 1 is, what's the difference between cosecant of 1/2 and the inverse sine of 1/2? Well, cosecant of 1/2 is the reciprocal of sine over 1/2. So in other words, cosecant of 1/2 is the same thing as 1 over sine of 1/2. Which is equal to 2.09. So in this case, 1/2 here is the size of the angle in radians. So 1/2 is like less than 1. So it's saying here that 1/2, the size of that, if this is pi, half of 3.14 is 1.5 something. So it's going to be somewhere in here. So it's saying, what is the ratio of not y to r, but r to y, the upside down, okay? So it's the size of the sine ratio is what you're solving for. So this is the size of the sine ratio, and in this case, 1/2 is the size of the angle. However, sine to the -1 of 1/2 is the inverse of sine of 1/2. In this case, you're saying a 1/2 is the sine ratio, and you actually need to solve for the size of the angle. So this is basically saying sine of theta equals 1/2, and you have to solve for theta. So now this is the size of the sine ratio, and theta is the size of the angle that you have to solve for. Okay, so in this case, you could do say theta, and so you do sine to the -1/2 into your calculator, and you get 0.5236. So this is the size of the angle that gives a sine ratio of 1/2. Now, the reason why this is more confusing is that radians are decimals and numbers. So they're not big numbers like degrees. In grade 11, it was very obvious if you had a sine ratio like 1/2 that that wasn't going to be the size of an angle, because our angles were normally like 30 degrees, 100 degrees, some much bigger number, whereas sine ratios cap out at 1. That's the highest they can get. So you have to be much clearer that you understand which is the size of the angle and which is the size of the ratio when we're working with radians. One last example. Here we have a sun passing through the atmosphere to sea level as seen below. So when the sun is at angle x from the earth, the value of y affects the temperature. So we can write y here in terms of x. So if this is the sun as it's setting, it's creating an angle here with the earth. Okay, so here is our angle. All right, and so we'll say that the distance between the atmosphere and sea level, we'll just give a unit of 1, because all we care about is the ratio. So we'll say that this is 1 as well. Okay, so we can write y in terms of theta. So if this angle here is theta, and this is y, okay, we can say that sine theta is just equal to 1 over y. So y, if we rearrange this, is equal to 1 over sine theta, which is equal to what we just learned, cosecant theta. So if we graph this, okay, from 0 to pi over 2. Now, why are we ending at pi over 2? Well, pi over 2 is 90 degrees, which is the most the sun can ever set. So the most that this can ever be is pi over 2, because it's not going to go negative. So we remember that cosecant here, between 0 and pi over 2, is curving down like a parabola, okay, ending at this point, okay, which is pi over 2, 1. So what does this mean? So I'm going to write it up here so you can see it. As x approaches infinity, or sorry, as theta approaches infinity, so as this angle gets bigger, y is going to increase, y is going to get to some very large numbers. This makes sense since the sun's ray must pass through more atmosphere as x approaches 0. However, this model assumes that the Earth is flat and with uniform conditions, so it doesn't assume very good things. It's not a very reliable model. As we get further and further here, it doesn't make sense for it to actually go to infinity. Okay, this example is in your textbook if you want to read it again in that context, if this is becoming confusing for you, or I can re-explain it in class. So thanks for watching, guys. Hope you learned a lot.